everybody. My name is Dominic Ferry. Joining me today is Tyler Creighton, and together we make up Team Iradion, whose project focuses on automatic laser optimization. So for a brief introduction to a laser, laser is an acronym that stands for light emission by stimulated emission of radiation. Although this may seem long and complicated, it's actually quite simple. A typical laser consists of what's called a lasing medium. In Iradion's case, this lasing medium is CO2, or carbon dioxide. When you apply a strong voltage to this carbon dioxide, it causes the molecules to become excited and emit photons of light. These photons of light then bounce back and forth between two mirrors that are located on each side of the lasing medium. As they do, they become further amplified until they are passed out of the laser as laser light. Our project focuses on the adjustment of these mirrors inside the laser beam. The adjustment of these mirrors are very important because the angle that they are set at heavily influences a lot of the laser's attributes. In fact, it can easily be the difference between a working laser and a non-working laser. In order to adjust the angle, the mirrors come with set screws on the back that the engineer can interact with in order to change the angle. When these screws are pushed into the mirror, it creates pressure on the mirror membrane, which can thus changes the angle. So that leads us to our project motivation. Mirrors are currently adjusted by hand using long screwdrivers. This method tends to be inaccurate and time-consuming. It also tends to be very dangerous since lasers can output up to 500 watts of power. And manually turning them requires you putting your hand next to a very powerful beam. Screws also tend to be over-tightened and under-tightened, which over time can bend, warp, or even break the mirror, thus greatly reducing its life in the field. Therefore, our best anticipated outcome is, instead of using manual adjustment, to have a computer do it for you, and to create a system that adjusts the mirror such that its reflection is within 100 microradians from the desired angle, to ensure that no screw is over-tightened and under-tightened, and to make it as hands-off as possible, thus to avoid all the dangers that comes with manual adjustment. And we are very happy to say that we did indeed achieve this best outcome.
To take a look at what we've done so far, we prepared a demo. Now, there's a lot going on the screen at the same time, so let's first ignore the monitor in the back. We can come back to that later. Looking up front, you can see all of the components that we've put together for our project. Primarily over here, we have the autocollimator device, which will be talked about later, but its main functionality is to track the current angle of the mirror. This is connected to our mirror mount, which houses our mirror for our tuning, which is connected to our 3D printed mechanical design. This design is our actuator that actually exerts the work needed to be done on our screws. It is controlled by these 3 stepper motors, which are controlled by motor drivers. These drivers are controlled by the FPGA, and the entire system is controlled from our C# program. Looking closer at the monitor, you can see several things. The first of which is our GUI. The user has several options to change various things about the program, such as max screw turns, motor speed, stepping, etc. Once the user selects their desired attributes and hits the go button, the program starts. It's kind of hard to see, but the white crosshair is the representation of the current mirror angle. The desired angle is the middle of this blue crosshair here in the center. First, our algorithm tries to line up the white crosshair with the vertical axis by turning multiple motors at the same time. Once it reaches the vertical axis, it'll start moving towards the center of the horizontal axis to meet in the middle of the program. As was previously mentioned, the best anticipated outcome for our design was to get within 100 microradians at the center. We have both met and exceeded this by having almost every single test be significantly greater than this. Every single run of our program has had our crosshair within 20 microradians of the center, where most are much greater than this.
So let's look at some of our key accomplishments. The first one of which is software. The user will be able to interact with the system through a very simple and intuitive GUI that displays the current position of the reflection, as well as allow the user to change various attributes of the algorithm. In order to measure the angle of the mirror, we use what's called an autocollimator. An autocollimator is a device that shoots a small laser beam towards the mirror membrane and then records where the reflection lands. If you shoot a laser beam at something that is angled, we know that the reflection of it is going to be somewhere else. Based on that position, we will always know the current angle of the mirror in real time. This information is then sent back into our software for processing. In order to physically turn the screws, we had to design and 3D print ourselves a mechanical actuator that is able to couple on to the mirror and turn all 3 screws. The device that does this, we use stepper motors. Stepper motors are small motors that take a full turn and divide them into discrete parts. Our stepper motors are capable up to 800 discrete parts, which is much more accurate than by hand, which causes very fine tuning. The entire system is adaptable to different mirrors, and we made sure to slot it entirely for all the motors so that you can move them back and forth. In order to drive the stepper motors, we use stepper motor drivers. These are devices that take some electrical input signals from our FPGA and converts them into signals that the stepper motors can understand and act upon. It also makes the system far more robust by providing voltage overload and current overload protection.
So our FPGA receives signals from our C# program and converts it into instructions that our stepper motor drivers can understand. The drivers then send the data to our stepper motors to control the system. The FPGA also records the number of steps each motor has turned, thus ensuring that over-tuning and under-tuning is no longer possible, extending the life of the lasers. The FPGA also communicates serially with the program, as does the autocollimator. Looking once more at our demo, we can see the amalgamation of all the parts come together. We have our electrical engineering components in our autocollimator, our stepper motor drivers in our FPGA. We have our mechanical components in our 3D printed actuator, and we have our software engineering components in the result of our program and GUI. Currently, the entire process takes several hours, but our program gets the entire alignment done in minutes.
So let's talk a little bit about what this could mean for Iradion. When we created our design, we were sure to make it as scalable and adaptive as possible to other devices and sensors. This means that instead of using an autocollimator to measure the mirror angle, we could also just as easily use a power meter to measure the power output of the laser, or a mode profiler to sense and detect the mode profile of the laser. This means that our system is scalable enough and has the potential to automate the entirety of the laser tuning process, reducing what is typically an 8 or more hour process down into just minutes, which can completely revolutionize the way lasers are tuned. So at this time, I would like to thank Iradion's engineering manager and our technical director, Robert Mikowski, as well as Dr. Sunak, the ELECOMP Capstone program director, for this amazing and rewarding opportunity. Thank you very much.
Thank you.